Okay, hello everyone. Welcome to our Cosmic Conversations talk and the last one for the semester before the exams start and everything. And today we have Amy. She's a new PhD student here, working with, as you can guess, probably Professor Petruccione. She did all her degrees at UKZN previously. She has worked on some quantum information stuff, and now
I mean, I'm interested in machine learning, like physics-inspired machine learning, but this is something like completely different. So
yeah. So
okay, thank you so much. Yeah, so thank you everyone for coming. I specifically chose this title to be a bit like have a bit of shock value. So if you're here because you thought like, what on earth is this talk going to be about, then it worked. So if I'd chosen a little bit of a less controversial title, it would have been ZX Calculus, Quantum Information in Pictures. And I'm really excited about this, so I hope I can get you guys all involved. So my journey with the ZX Calculus really just started 3 weeks ago. We went on a trip to ICTP, which is a center in Italy, and we participated in a hackathon there. And there we had some presentations from a professor called Bob Coecke, and he's the sort of father of ZX Calculus. So just as a testament to how really easy this is to learn, everything that I'm going to show you today, I managed to learn in just 3 weeks. And this is like actually a really powerful formalism, because everything that you can do with the usual quantum information processing, like circuit diagrams, Dirac notation, you can do that all in this ZX Calculus, all with cute little pictures and spiders, as you'll see in a few minutes. So just to bring everybody onto the same page, this is the famous Stone-Gerlach experiment. And they send silver atoms through an inhomogeneous magnetic field. And if the particles had behaved how we expect them to behave classically, so that they could have any possible angular momentum, we would expect to see some sort of picture like this, where the angle of deflection is kind of continuous. But what they really observed was this discretized behavior. So either the silver atoms went up or they went down. And this is kind of at the heart of the difference between quantum mechanics and classical mechanics. So we can kind of label the particles that went up as like up particles and the particles that went down as down particles. And what went in is some sort of unknown state. It's like a superposition of having gone up or down. And these alpha and beta factors here correspond to like, what is the probability that you went up? What's the probability that you went down? So that's really all you need to know to understand everything that's going to come in the rest of this presentation. So what can we do with this? Well, in classical computing, we use bits, which can either be 0 or 1. But this kind of quantized behavior that we observe in nature, so we also see this like for photons, we can create quantum bits, which we call qubits, and they can be in any superposition of 0 and 1. And this is very useful for information processing. So normally, when people want to learn something about quantum information processing, there's like a big barrier in the way. You know, first you need to learn a lot of linear algebra. You have to learn about Dirac notation, probably some quantum circuits if you want to do quantum computing. But the ZX Calculus kind of gives you a shortcut around this barrier, and you can do all of this just using these simple diagrams. So here I'm just summarizing a kind of timeline of ZX Calculus. So around 2007, Bob Coecke and some of his PhD students in his group at Oxford, they developed this diagrammatic calculus, and they were able to show that it's sound and complete and it's universal. So any calculation that you could do in the usual notation with matrices, you can also represent diagrammatically and come to the same solution. And in 2017, with Alex Kissinger, he published this textbook, Picturing Quantum Processes. This is really a university level textbook, but late last year, they published this book, which I have a copy of, you're welcome to borrow. And it really explains quantum mechanics in a very, very simple way. I mean, you could give this to your young niece or nephew, and they could learn all about quantum mechanics. So it's really a fantastic invention. So how does this work? Well, everything in ZX Calculus is done with wires and boxes. And in these diagrams, you should read time as flowing from top to bottom. And a wire is like a conduit of a quantum particle, and you can have these boxes. So you have, say, n quantum particles going into a box and m coming out, and this box can represent any operation that you would do on your quantum states. So a unitary operation, a measurement, whatever you like. So this is the language of ZX calculus. And just some little technical things. If we put two wires next to each other, we understand that to mean the tensor product between the two wires. And whatever wire we draw, we can deform it however we like, as long as we preserve the number of wires going in and out. So if we have two wires going in and two wires going out, we can deform those wires in between however we like, as long as we keep the two going in and two going out. So you can deform them. And then we have some special boxes. So for example, a state, which is like the usual ket. So that's why we use this triangles, kind of resembles the usual ket in Dirac notation, if you're familiar with that. So a state is something where we only have wires going out, and an effect is something where we only have wires going in. So this is like a bra. And if we put a state and an effect together, we're basically doing an inner product and we get a number. So that's all we need. We can build processes, we can build effects, and then if we turn that upside down, we build a state, and we can construct numbers. So two really important, or the two most important boxes in the ZX calculus are affectionately called spiders, because they resemble little spiders. Yeah.
Sorry, in the first picture you showed with the state and the effect, two of them are closer than the other. Is that to represent that those two are special, or is it just an orientation?
These two?
Yeah, those two are closer together. Is that?
No, that's not important. It's just to show there's like some arbitrary number going.
Oh,
yeah.
right. There's not just 3 wires there.
Yeah, no. It's like this is a ... So you might have like 10 or 20 or even just 1. Yeah. Okay. Okay, so the two most important boxes in the ZX calculus are the spiders, and they come in like 2 varieties. So here I've just decided to distinguish between them with like green and purple, but you can pick whichever colors you like. So the green spider is the Z spider. And if we write what it does in this Dirac notation, it's written like this. But if you've never seen this before, it doesn't matter. Just know that we have 2 types of spiders. One of them is a Z spider, and the other is an X spider. So you notice here the structure is the same, except for the X spider, instead of having the 0 states, which are the eigenstates of the Z measurement, we have the eigenstate of the X operator, so the plus and minus states. And we can also put little decorations on the spiders if we want. So we can draw a little, like an angle, alpha and beta, and that just corresponds to a phase between the 2 outer products. So like for this green alpha spider, we'd have 0, 0, 0, 0, 0, 0, and then each the I alpha 1 on 1, 1 on 1. And similarly for the spider. And then I've put this little key here at the bottom just for people who are familiar with Dirac notation and you want to just remind yourself which spider is which. So the green spider goes with the eigenstates of the Z, and then the purple with the eigenstates of X. So now we can look at some like special cases. So let's imagine our spider just has 2 legs. Well, that's the same as doing nothing. It's just the identity operator. So anytime we see a plain wire, we can essentially add plain spiders to our heart's content or remove them. And what about just a spider with 1 leg? Well, that's just a state. So if we have just a plain green spider with 1 leg, that's simply the plus state. And if we have a plain purple spider, that's just the 0 state. And of course, I can flip this diagram upside down, and now I have the bra plus and the bra 0. So this is something more interesting. So now we can construct the Bell states. So this is the first Bell state, and it's represented simply by a cup. It's just two outgoing wires. And then of course the Bell effect is just the flipped version of that. And some sort of familiar gates, if people have seen anything for quantum computing, we have a phase gate, a NOT gate, so that's like a bit flip. So if we go in with a 0, we change it to a 1. If we go in with a 1, we change it to a 0. And we also have the Hadamard gate here. And the other gate that's very important in quantum computing is a C0 gate. So this is a controlled NOT operation. So this is our like control state, and this is our target state. So if we input a 0 state here, the instruction or what this should do is it should do nothing to the target bit. However, if we put in a 1, then it should perform a bit flip on the target state. So I'll convince you in a moment that this really does do what I'm saying that it does. So now that we have these spiders, we can actually construct any crazy diagram that you want. You can really just draw whatever you like, and this is a valid diagram. But then, of course, the next question is, what do we do with this? So we probably want to simplify this to understand really what on earth does this really represent as a circuit. So for that, we use the spider rules. So the first rule is the fusion rule. So if you have two spiders of the same color, you can simply fuse them and their phases just get added up. And what's important here is that if you had n legs ingoing and m legs outgoing, that's you preserve that in your resultant spider. So whatever legs they shared are just absorbed into the body of the new spider, let's say. So that's the fusion rule. And this only works if the spiders are the same color. So if you have two green spiders or two purple spiders. And because of this fusion rule, you can understand this in two ways. Either you see this as like we just put a plain spider on here, which is just the identity. So this is equivalent to doing nothing. And by deforming this leg, just pulling it down in space, what we've done is we've changed one of this spider's output legs suddenly into an input leg. So you can do that if that makes it easier for you to simplify your diagrams. And of course, you could also see this not only as identity, but also this spider would be absorbed into the bigger spider if we were going to go backwards to this picture. So what if two spiders of different colors share some legs? Well, if they share an even number of legs, then the legs fall away. And there's a very cute diagram in the book where he explains this as the spiders don't like each other and each one gives like a punch to the other spider and their legs fly off. So if that helps you remember the rule, that's how it works. So in general, this is called the Hoff rule. So if you have any two spiders with opposite colors, you can drop even number of legs between them. So they sort of defuse, if you like. Okay, and then these are our 4 Bell states. So I've already shown you this first Bell state, but these are the other 3. And I hope that with the rules that I've shown you, you can kind of convince yourself that the diagrams on the top are equivalent to the diagrams on the bottom. So let's take this left-hand one. So here in this case, this green spider would fuse with this green spider. And now we have one green spider with 2 legs, which is just the identity, so that disappears. And the same here, this purple spider will fuse with the other purple spider, and now we'll have a purple spider just with 2 legs, which is the same as doing nothing. So we end up with this diagram here. And then here we had pi remaining because when these 2 spiders fused, their phases sum to pi. So if it's a plain spider, we just understand that as phase 0. Okay, so those are the 4 Bell states, which are going to come up a little bit later. So what happens if we have a cup like this and we send in a 0 state? Well, this kind of corresponds to our intuition of what this cup represents. So the Bell state says that if say Alice over here measures something, whatever she measures, whatever the outcome of her measurement is, Bob is guaranteed to see the same result on his side, at least with a plain cup. So if we send in this purple spider, we see it's almost like the spider duplicated this information. So this is not copying, but if we send in the 0, it will send a 0 to the left and a 0 to the right leg. And then similarly for if we have a purple spider with a green spider. Okay, so now I'm going to use this rule to convince you that the diagram that I showed earlier really is the C0 operation. So let's take the C0, which is just these 2 spiders of opposing colors joined with 1 leg, and let's send in the 0 state. So let's see what happens. Well, it arrives at this green spider and it has 2 legs. So a purple spider is sent up the first leg, and then a second purple spider is sent towards along this wire to this purple spider. And then we can use the fusion rule to just join up these 2. And now we have a purple spider with two legs. So it's just the identity operation. And we see this control bit didn't change. It's still purple. But what happened on the second wire is nothing. So that's the first case. Second case, we can send in a 1. So this is a purple spider with a par phase. And if we send that in, it gets copied. But now this par has arrived on the wire on the right-hand side. So we do a not operation if we send in a par. So that's the control not. What if we have some more like exotic diagrams? So now we've got this sort of checkerboard pattern of spiders, and they're all sharing legs. What do? Well, we can put 2 spiders on these 2 bottom wires, because that corresponds to doing nothing. We can also give them 2 legs, because this is the opposite of the half rule. So adding 2 legs is the same as the legs not being there at all. And then we can unfuse these spiders. So now we have a green spider with showing 1 leg with a purple, and another green with a purple. And then we can identify this as the swap operation. So for people who have seen something about quantum computing already, you know, like 3C knots in alternating like this performs a swap operation. But if you don't know this, you can just trust me that this gray box here corresponds to a swap. So all we do, we just swap the wires, and that's all. So this is the bi-algebra rule, and a sort of simple way to remember it is if you have this pattern, you look at the 2 spiders of the same color that are opposite each other, you fuse them, and you swap their color. So here, green fused with green and became purple, and purple fused with purple and became green. And then you just have to keep track of what wires were connected to what. So maybe you would label these 1, 2, 3, 4, and then you check, okay, 1 was connected to this green one that became purple, so you connect it up to the purple one. But you can also use these swap rules that I've shown already. So now we have a sort of more exotic version of what I just showed you. So if you see something like this, well, it looks a bit daunting, like how do you deal with this? Well, no problem. You can just deform your diagram however you like to bring it into something that's familiar. And then you can add some spiders to make things easier, so you can identify a swap, or you can use the rule that I just explained where you fuse these 2 and change their color, and fuse these 2 and change their color. And you can convince yourself that what we finally end up with is something like this, which we can redraw into a nice simplified diagram like this. So we turn something really seemingly very complicated into something that's actually really quite simple. Okay, so I've kind of shown you some of the like main rules that you need for ZX calculus, and now I want to show you like some typical quantum mechanical processes that you would normally have to understand using quantum circuits and after learning like a whole bunch of linear algebra. So I hope like at least there's some people in the room that maybe don't know about these topics. Is there at least? Okay, cool. So I'm not going to bore some people. Okay, so let's imagine we have 2 people, Alice and Bob, and they each share 1 qubit in an entangled pair. So this cup state represents the entangled qubit, so one of the Bell states, and Alice has one of these qubits, and Bob has one of them. Okay. And Alice has, and they're very far apart. They're in opposite ends of the galaxy to each other. And Alice has a state psi. She just has one of them. She doesn't have a way to copy it. She wants to send it to Bob. So what should she do? Anyone want to take a guess?
Can you repeat that?
So what should Alice do to send psi to Bob? The stupidest thing you can think of. Okay, but yeah, sure. But she doesn't know what psi is, because if she wanted to know what psi was, she'd have to measure it. But if she'd measured it, it would destroy the state. So she can't do that. Sure, but what change should I make to this diagram to just send it? Yeah? Yeah, just connect the lines. Just connect the lines up. Yeah. No, it's really that simple. Yeah, so Alice just puts a cap on it. She just connects up the lines, okay? But, okay, so now Bob has psi. So this seems like we communicated faster than the speed of light. So what happened? Well, it turns out that when Alice puts this cap on, she's performing a measurement. So actually, there's 4 possible things that could have happened on Alice's side. Either she could have put a plain cup, or she could have had a cup with a green pie spider, or a purple pie spider, or both. So these things, Alice does not have a control over which one of these 4 things occur, and it's completely random. So she puts her cup on, and she phones Bob, and she says, Bob, this is my measurement outcome. So in this scenario, she measured 0, 0. So she phones Bob, and this is classical communication. So this happens at the speed of light, at most. And then Bob knows on his side what he should do to receive psi. So essentially to correct for whatever error Alice introduced. Yes?
Are the loops in the wires just artistic effect?
Are the
loops in the wires just for artistic effect?
Yeah, so the loops are meant to represent like a classical phone call.
That's
so yeah. So this doesn't represent classical, like quantum information. This is just literally Alice picking up the phone and phoning Bob. So let's look at a different scenario. So let's say Alice measured 1, 1. So she had the 4th bell state. Then she phones Bob and she says, Bob, I measured 1, 1, and now Bob can correct for that. So if you imagine removing these curly wires and we fuse the purple with the purple, and then this purple fuses with this purple, so then we get pi plus pi, which is 2 pi, which is just a phase shift of 0. So we did nothing. So you can see how Bob needs to perform this operation in order to make sure that he corrects for whatever error Alice introduced with her measurement. Okay, and then we can sort of represent all the possible scenarios by just overlapping these 2 images. So Alice could measure 0 or 1 for her green and 0 or 1 for her purple, and she tells Bob what to do. So that's quantum teleportation really in a nutshell. And this is what the circuit looks like. So I hope that you're kind of convinced that seeing this diagram is a lot more intuitive than seeing this circuit. The circuit's not at all obvious what's happening unless you already know what the circuit does. Okay, so let's do one other example, which is quantum key distribution. And I chose this example specifically because there was a nice demonstration of quantum key distribution in the 3rd year lab. It was like a few weeks ago. And when the presentation was going on, I realized that I thought I understood this protocol, but I really didn't actually, because I didn't understand why the eavesdropper was detected a certain number of times. So I decided, you know what, I'm not going to look into the literature. I'm just going to draw some diagrams and see if I can convince myself of what's really going on, just given the sort of vague knowledge I knew of this protocol. So I'm going to hopefully convince you as well how this works. So Alice and Bob, they share an entangled state again. So Alice has one of the qubits, Bob has another of them. And they want to generate like a secret key that they're going to use to encrypt their messages in the future. So they can use this Bell state to generate like a random, if they repeat this experiment many times, they can generate a random string of bits. So independently, Alice and Bob each choose either green spiders or purple spiders, and they don't discuss it beforehand, they just do it completely at random. So sometimes Alice will choose green spiders, sometimes Bob will choose purple spiders, but in the instances where they happen to choose the same color, then we guarantee to see the same measurement on both sides. So if Alice measures 0, Bob will also measure 0. And if Alice measures 1, Bob will also measure 1. So this is a way for them to generate like a secret key. So let's say we have Eve now, and Eve wants to eavesdrop on what Alice and Bob are doing, because Eve wants access to the key so she can decrypt messages going forward. So Eve doesn't know what Alice and Bob are going to choose. So at best, Eve can also just pick a random color. She can either pick green spiders or purple spiders. So let's say Alice, Bob, and Eve all happen to choose the same color spiders. Then in this scenario, Eve goes undetected. So Alice cannot tell that Eve was there, and Bob cannot tell that Eve was there. Because if Alice measures 0, she just creates a 0 state and sends it through to Bob. And if she measures 1, she sends 1 through to Bob. So there's no way for them to tell, because if we kind of fuse all our spiders up, we see everything comes nicely just to green balls, which are just numbers. But let's take the scenario where Eve happens not to choose the same color as Alice and Bob. Well, in that case, she's going to basically disturb the situation, and Alice is going to measure 0 or 1 with a 50-50 chance, and Bob is also going to measure 0 or 1 with a 50-50 chance, and there's no correlation between what Alice measures and what Bob measures. So there's a chance, so in half of the situations, Alice and Bob just by accident had the same bit string. They both measured the same 0, 0. But in half the cases, Alice will see 0 and Bob will see 1, or Alice will see 1 and Bob will see 0. So what Alice and Bob can do is when they finished repeating this experiment many, many times, let's say they do it, I don't know, 50 times, they can phone each other and they can say, okay, well, first they ascertain in which cases do they both choose purple or both choose green, and they discard all the other scenarios where they didn't, where they used different colors. And then of all their experiments, they select a subset of them and they check, did you, I saw a 0. Did you also see a 0? I saw 1. Did you also see a 1? And they know they can detect the presence of Eve if they see this mismatch between what they measured. And in this case, so Eve has like a 3 in 4 chance of going undetected. So from the 2 scenarios from here where she goes undetected and the 1 scenario from here where she goes undetected. So she has a 3 out of 4 chance to go undetected. But if we repeat this experiment many, many times, say even something silly like 20 times, then there's only a 0.3 chance that Eve will go undetected. So you can see if we did this millions of times, the chance that Eve will go undetected is like really, really diminishing. So yeah, so that's just a taste of some quantum cryptography. And I really hope I've convinced you at least of the sort of pedagogical value of this, is that if you wanted to explain quantum mechanics to a small child, this would be the way to do it. So it's really great. And I want to emphasize that whatever you can do with normal calculations, you can also do in this diagrammatic language. And there's a nice anecdote of a story that Bob told us, is that they actually plan to take some high school students and teach them ZX calculus and then get them to write the same exam as Oxford undergraduates to see who actually performs better. And he seemed pretty confident that the high school students would do better, but I guess we'll have to see. And also this is like at the moment, currently the state of the art for quantum circuit optimization. So you can feed in your circuit, convert it to one of these diagrams, simplify it and convert it back to a circuit. So that's really, really cool. And another application is quantum natural language processing. So I would love to go into more detail of this, but there really isn't, I think, okay, there might be time, but maybe later we can go into it. But it's very, very cool, because what happens is when you construct these diagrams, they actually coincide with like the grammar of language, and you can build quantum circuits where your question is like a circuit and you encode all your sentences in another circuit. So it's very flexible. You can essentially plug in whatever question it is that you want to ask. And they also have the really big advantage that these are not black box algorithms. So you can really explain why did you get a certain answer over another answer. So it's very, very cool application of this. And then another one is, this is a good way to visualize quantum error correction algorithms. So there's some like useful links if anyone's interested. And I just included one reference here. If you're really still not convinced that this is an interesting thing to learn, if maybe Peter Shaw's sort of endorsement of it is enough to get you interested. This is a very, very famous person in quantum information processing, and he recently published this paper on the archive. Yeah, so thank you so much. And yeah, I hope you found that interesting.
Great, thank you very much, Amy. If anyone has any questions, they can ask them now.
How do you use the left-right basis? Or the y, or because the zx calculus, I'm assuming it's called zx because it represents your z or your basis for the z gate and the x. How do you use the y or the left-right basis?
Okay, well, we can just see, we can just transform that. So, okay, so let's go back to what the usual spiders look like. Okay, so it turns out that these spiders actually correspond to like rotations in the block sphere. So if we just look at spiders with 2 legs going in and 2 legs going out, so if we add a phase to them, it's like a rotation. So let's say we input a plus state, which is along the x-axis. If we want to get a y state, then we just rotate that 90 degrees around the z-axis. So you would do, let me think for a second, you would do a...
So green pi over 2 is a plus, or sorry, or right, whatever.
So a green pi over 2 with 2 legs going in, 2 legs going out would be a rotation around the y-axis for pi. It would be pi, yes, pi over 2. Sorry, I just have to think because there's always like a half that comes in there somewhere. But yes, it would be pi. So if you wanted to get like the y state, you would input like a plus and then do this rotation around z. But I mean, you could also do it a different way. I mean, you could use the 0 state and do a rotation around x. So there's multiple ways to do it. But yeah. Okay.
The other question about you said it's quite flexible inputs and outputs, right?
Yeah.
Like you can reform wires. Can you say a little bit more about that?
Yeah, sure. I actually had a slide that I took out that kind of alludes to why this is like a universal way to write things. So so we can construct like any state in this way, just like where this box represents some sort of operation with a bunch of spiders inside there. So that represents a state. But we can like transform this by just bending some of the legs, essentially. So we can, there's like a link between states and operations. Yeah, does that answer your question? Okay.
Are there situations in which you have the same number of inputs and outputs and the same number of boxes with the same sort of patterns where you can't deform the one into the other one? Can you represent like quantum topology effects with?
So like it's like you have 2 diagrams, but you can prove that there's no way to transform one into the other. Is that
like essentially things like
yeah, I mean that's a really interesting question, and I'll admit I don't know the answer. Yeah, I'm 3 weeks in, but if you want to figure out the answer with me, I mean that I'd be really interested to know the answer to that question. But yeah, there must be some rules. So I think where this whole theory originated from was actually category theory. So if you really want to go like deep into the older literature, I think there are papers where it's a lot more, the maths is a lot heavier. Yeah.
So probably similar, probably not. You know that all of these wires can be represented using knots, like the mathematical.
Or like a logic.
Yeah.
Yeah.
It's topology where people use knots, right? That's the type of topology.
Yeah.
Yeah, I'm not sure. I mean, a knot is like not a universal gate. So, I mean, I guess that they are.
I mean, not like meaning there's ways like to represent like a Boy Scout knot.
Oh, okay. I guess in this scenario, knots don't really mean anything because it's just like you've deformed the wire into a knot. So,
I was wondering like, what if there's a way that you can somehow represent certain structures of gates in ways of knots? So maybe if you had what if there was a way to like represent the gates and as a knot in a way that you know that a certain circuit can straighten out to a different one?
Yeah, I mean that's a really cool idea because I'm like picturing something like you have like 2 caps and a cup, and then you like do something. I don't know. You'd have to intertwine them, I guess, something like this. And then you could ask, like, is there some way? Yeah, I mean, it's an interesting question. I'm not sure.
I remember you mentioned that like wires crossing each other as a view. You said it's not theory in 4 dimensions.
Yeah,
So
sure.
In this case.
Yeah.
You could do a personal helpful.
Yeah. Like, for example, if you have a spider that just has a leg like this, like a circular leg, this is nothing. This is just identity. It just gets absorbed into the spider. Yeah.
Actually, the wires can like move through each other, but they're meant to be.
Yeah.
Like there should be some combination of spiders.
Like, what if there's a way you could represent a gate as a way of twisting the wires?
I guess that wouldn't be possible because twisting the wires just converts your wires sort of into like cups and caps and not really spiders, whereas spiders are sort of the magic ingredient that you really need to represent everything. So, but yeah, it's a cool question.
I wanted to ask if this self-loops are allowed.
Yeah, so that takes care of self loops. So if you have any self loops, they are doing nothing basically. Yeah, but where this is useful is like, say you want to transform your diagram somehow, you can kind of create one of these loops where it's convenient for you and stick a spider on it. So they can be useful to use these kind of self loops.
And I imagine like doing all of this by hand must be tedious. So
Yeah, they definitely are. I mean, like, for example, they have this like TCAT package that they've developed at Quantinuum, so you can do it sort of efficiently, computationally. Yeah. Don't ask me how, because I don't know, but it is possible. Yeah. What they don't have yet, though, is a nice way. I mean, they have some visualizations of these things that are automatically generated, but they're not very nice. So if anyone's really excited about this, there's a gap in the market to produce some nice software to visualize these things nicely. Yeah.
Yeah, I also have a question. Is there like a unique minimal form given a diagram that one can convert every diagram to?
Yeah. Sure. I'm not sure, but I would imagine that it's something similar to the situation that you get with like quantum circuits like C naughts but probably you can just, I guess it depends what you mean by minimization. I mean, if your goal is just to get the fewest spiders possible, then there probably are some like lower limits to the number of spiders that you can have, something more than 2. But yeah, I mean, it's really amazing like how small these diagrams get. You can convert like very complicated circuits into like three spiders, something like that. Yeah.
Is that maybe something to do with the completeness? So in other words, any arbitrary operation that you perform can be represented with these, and then if there's like a set of 3 universal gates or something in quantum computing, right?
Yeah. Yeah. Well, yeah. Yeah. Well, it depends. Yeah, it depends sort of what universal set that you want to use. So like, let's just say you want to just use Toffoli gates, then you would end up like with only spiders that look something like this. I guess this would be purple, and then you have a green and a green, and then I think you would make a connection like that. So you could convert like all your diagrams into something that look like this. So that's actually something that's really cool about it, is because of this like deformation thing, you can form it into something that makes sense for the quantum hardware that you're using. So like, let's say you're using like trapped ions, and maybe there's some specific gates that you can implement like with less noise. You want to obviously use more of those gates, so you can transform your circuit into something that uses those gates. Yeah.
Any other questions?
Thank you.